Hello, this is the next video in a playlist that I'm calling probability measure, and in this video we're going to look at a complete measure. Now later in this video we're going to refer to this video, which is earlier in the playlist, and I'm going to call it BV1, background video 1, and it's a probability measure on a field, can be extended to a probability measure on a sigma field, specifically the minimum sigma field generated by that field. Now the definition of complete is this: a measure mu on a sigma field F is said to be complete if and only if A is in F and has measure 0, we have all the other subsets of A also in F. Then the measure on field F is said to be complete. Now mu is important because, and F is important, or the sigma field is important because some measures of A will be 0 and some measures of A will not be 0. So complete is specific on the measure on that sigma field. The completion of a measure space, omega, F, and mu. So since it's a measure space, we know that this is a sigma field. And it's defined as follows. Let F of u, right, the complete measure, right, depends upon the measure mu, be the class of all sets A union N, where A ranges over F, the sigma field, and N over all subsets of measure 0 in F. Then that's called a completion of a measure space. Now, F of mu is a sigma field including F. Okay, so to be a sigma field means omega has to be in it, and if B is in this completion, then the complement has to be in it, and also this infinite unions have to be in that completion too. So let's prove those. Now first, let's prove that omega is in F of mu. And omega can be written as omega union the empty set. Now we're at omega is in F, and the empty set is definitely a subset of M where M has measure 0. So the omega's in F of mu. Let's let B equal A union N, which an element of the sigma field. N's a subset of M in that sigma field, and mu of M is equal to 0. Then the B complement, which is equal to A union N complement, right? B is just that, but this is A complement intersect N, and that's equal to this, and I'm going to leave you with the details. It's not hard to go from here to here. And then this we know. So M is in F, and A is in F, and it's a sigma field, so its complements are in it, and finite unions are in F. So this is in F, right? So this lives in F, and this right here is really small. So A complement is in F, and since M minus N is a subset of M, which has measure 0, then B complement has to be, which is this, it also has to live in the completion. Now B1, B2, are elements of the completion. Let them be that. Then let BI equal AI union NI, right? Since it's a completion, we know that it can be written like this, where AIs are in the sigma field, and N is a subset of MI, which has measure 0. Then the union of these BIs, which is the union of this, actually can be written like this. But note that this union, infinite union of AIs, is also in the sigma field, right? Has to be, and the measure of this infinite union is less than or equal to the measure of the infinite unions of all the mi's, which is less than or equal to the sum of all these measures, but all these measures are zero. So that says this measure is zero. And that says this infinite union has to live in the completion, f of mu. Now let's look at a theorem here. The completion of this measure space, I meaning this, is complete. So let's prove that. M is a subset of A union N, which is an element of this completion. Right? Now A is in the sigma field, and we're going to let it be 0. Right? And N is a subset of B in the sigma field, and the measure of B is 0, right? And now we have to show that this is also in that completion set. So then M, which is a subset of A union B, right? Because N is a subset of B. So this is bigger than that, and that's in this, which has to be in this, but that's in part of the sigma field. And so the measure of A union B is less than or equal to the measure of A plus the measure of B, but both of these are 0, right? So hence, M has measure 0, right? This is, so the measure of M is less than this, which is less than this, which is 0, and so M has measure, which means it's in the completion of f of u. Now the theorem, this is in reference to BV1. We created a measure, an extension called mu star onto this set H, which was a nice extension, and it actually created a probability measure on H. This is a completion of this measure space where mu, and this is the minimum sigma field generated over the field F that we started from, and mu star. So to prove this, we need to show that H is actually the completion, f of mu. Right? And then we're done. So then this would be a completion of that, where f, of course, is the minimum sigma field generated over F, the field. Now let's let A be an element of H script, and by definition, mu star and mu star complement, we can find sets Gn and Gn prime that live in the sigma field such that Gn's a little bit bigger than A, Gn prime, and Gn is a little bit less. It's a subset, and then A is a subset of this, right? They close down onto A in limit. So, and the measure of Gn goes to the measure of mu star A, and this measure goes in limit to mu star A, right? The measure of this goes to the measure of that. That's the way we define mu star on H. Now let G be the infinite union of Gn, and G prime be the infinite intersection of Gn, right? Because these increase to A, and the Gn primes decrease to A. So since A can be written as G union A minus G, right? Because G has to be, it increases this way to it. And so G has to be a subset of it. So A can be written like this. It's essentially take out, you have A, take out G, but then union it back, so that has to be A, right? G is an element of the sigma field by definition, right? Sigma fields contain the infinite unions. A minus G is a subset of G prime minus G, right? Because this one, G prime is a little bit bigger than A, so this has to be. But G prime and G are both elements of the sigma field. So that means mu star of G prime minus G is less than or equal to mu star of Gn prime minus Gn. But these they squeeze down to 0, right? The difference goes to 0. So that means mu star g prime minus g is equal to 0, right? If this limits to 0 and this is less than that, it has to be 0. Now let A be an element of f of mu star, right? And it's mu star because that's our measure that we're looking at. So A is an element of that. Now let B be an element of f of mu star. Then B can be written as the union of A union N, where A is in the sigma field and N is a subset of M, which lives in the sigma field but has measure 0. Now since the sigma field is a subset of H, and we proved that in the previous video, we have A is an element of H, right? If A is an element of this, which is a subset of that, so A has to be in H. And since this measure space is complete, we have N in H. Hence B has to be in H. The completion. And we're finished. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like it, subscribe, so you don't miss the next one. Thanks, bye.